Now we're going to run through all of the equations that are necessary to actually do a full great circle sailing, what each of them are for, and then all of the components that go into them. So you kind of have that idea in advance of all of the steps that you're going to take. So the first thing you do is you calculate the actual distance along the arc that you're going to be sailing. So if you're going from here to here, how far total is that distance? This is not necessary for any of the following equations. Like, you're not going to need your distance for calculating anything further, but it is practically necessary in that that would be how you determine whether or not it's even worth it to do a great circle sailing. If you calculate your distance by great circle sailing to be like 2,000 miles, and then if you calculate it by Mercator sailing to be 2,050 miles, like, it is more efficient to take the great circle route, but it might not necessarily be worth the effort. It's not a huge difference. Now, I also just made those two numbers up. I don't know if it's those are necessarily accurate. There will be a lot of situations where the difference is really like 2 miles. So in that case, yeah, why bother? So that's what the purpose of this equation is. The next step you would take would be to calculate the course angle. Now, this is not like the course you're going to follow. Obviously, as you're following this arc, you're going to change direction constantly. But what the course angle is the starting course you would be on from your very first point. So if you were starting here, going here, what direction is the great circle route pointing right here, right where you start? Where do you need to face to follow along the track at the very beginning? That is not in and of itself important, except for the fact that it will then go into nearly every other equation following. So this is a necessary component of everything that comes after. Now, like I said in the previous video, your ultimate goal is to locate the vertex, because that's the only point that actually matters. That's where the whole circle is defined off of. So then your next equation is used to calculate the latitude of the vertex, so that you could place its, north-south position on the chart. Next, after that, you'd be finding the DLO of the vertex, so the difference of longitude of the vertex away from your starting location. That's because you can't just automatically calculate its longitude on its own, but what you can do is find how far away longitudinally it is from your position, which is your starting location, and then from there you can apply that distance away to find your vertex. And this is actually usually for me the hardest part of the problem, just because it's not necessarily obvious in some of those weird cases where you're going more north-south which direction you need to apply to go to the vertex. Sometimes that gets confusing. Then once you've done that, you'll actually find the longitude of the vertex as well, and you'll be able to locate it on the chart. The last equation you use multiple times over to calculate the latitudes of the various waypoints along the track. You can just pick whatever difference of longitude away from the vertex you want, and therefore automatically choose those waypoints' longitudes, but you have to use this equation to calculate their latitudes. So now, running into what these equations actually are, I'm going to just read them off and explain each factor that's going into them. So you can hear for the distance formula, the cosine of the distance is equal to the sine of latitude 1, so your starting location, times the sine of latitude 2, your ending location, plus the cosine of latitude 1 times the cosine of latitude 2 times the cosine of the DLO. So obviously what that means is the first major pieces of information you need are the latitudes of both your starting point and your ending point, and the difference of longitude between them. So if you've got here and here, and here's the equator down here, you don't need their longitudes, like their actual longitudes. You don't need that this is 60 degrees east and this is 15 degrees east. That doesn't matter. But what you do need is this point's longitude and this point's longitude, and then the distance between, or sorry, this point's latitude, and then this point's latitude, and then the distance between the two. And once you have those three values, then you can start working on actually calculating this, which is the course angle. That's what you're finding. So, oh no, sorry, the distance in arc between the two. After having found it's the first latitude, the second latitude, and the difference of longitude. Now, what's important to note about there, even though you see, latitude and you see DLO, in previous sailings, you've seen DLO and been like, okay, so I have to convert it to minutes. That's not true here. Like I said, great circles are the point where we're transitioning from thinking about a single map on or a single area of the Earth to thinking of the Earth as a whole. So now that we're thinking of it as a whole, you're not converting this to minutes. All of these are in degrees. They're in full degrees. So when you find your first latitude, let's say it's 12 degrees 30 minutes north, you don't care about this notation here. This is now 12.5 degrees. And it doesn't have a north-south because you're plugging it into a calculator, so its northerly value doesn't really matter. It's just 12.5 degrees. If your ending location is like 15 degrees 45 minutes north, it's now 15.75 degrees. And now, as just to note, if instead of that you were doing this, and here's the equator, and you're going from north to south, let's say 12.5 degrees, this wouldn't be 15.75 degrees south. This would be negative 15.75, because we need to put it into the equation. And you can't have just south. That doesn't mean anything to the calculator. You have to just put a negative sign in front of the degree value if you're going into the other hemisphere. Now, if you're starting from south to north, that's fine. That doesn't make a difference. But now the northerly values would be negative because you're starting, where you start is positive and where you end is negative if it's in the other hemisphere. So you convert your latitude to full degrees. You convert your other latitude to full degrees. You switch it to negative if you pass into the south when you started in the north, or if you pass into the north when you started in the south. And then your DLO, if let's say it's I don't know, 6,000 miles. If it's 6,000, that was 60,000. If it's 6,000 nautical miles, well, you now have 100 degrees because you don't care about, remember, nautical miles are equivalent to minutes, and you don't care about minutes. Or in this case, the DLO, never mind, it would probably be something like 100 degrees, 30 minutes. Again, that comes out to 100.5 degrees because you're writing this in degrees as well. So you've got the first two latitudes, the latitude of the beginning point, the latitude of the ending point, and the difference of longitude between them. Then when you come down to your next formula, you're still using those same numbers because, again, the distance doesn't get used for anything else. So now you're still plugging in the sine of the DLO, the difference of longitude, divided by the cosine of L1 and the tangent of L2, minus the sine of L1 times the cosine of the difference of longitude again. I know these equations are long and painful. All of that is equal to the tangent of the course angle. Remember, it's not your course, it's not CN, it's CA. So you have to remember that. And you also have to remember, let's say it says 60 degrees, that's technically 60 degrees from the vertical here. And if it says negative 60 degrees, you then have to flip it around by adding 180 degrees to get it over here. If it's negative, you need to be aware of that because that means your vertex is somewhere over here, which it wouldn't be in this case, but it would. Then it would be like negative 60 degrees. You'd have to add 180 because it would be pointing this way. And you would have to flip that around to point this way. But then after you add 180, or well, That would be to find your true course. No, you still, I'm fuzzy on the details, but you still add 180 regardless, and then use that as your new course angle, making sure that it's still under 90 degrees, or not up to 90 degrees, because it has to be, within that 90-degree angle to work for trig. Then once you finally find your course angle, again, most of the time you won't have to worry about that at all. Most of the time you'll just be going like this. You're looking for your latitude of your vertex. So you're plugging in the cosine of L1, just like you used from up here, and the cosine of your course angle. Because remember, your course angle is defined off of L1, is defined off of your starting location. The course angle is where you're pointing from there. So if you use it and its latitude, you can then project yourself forward to get the latitude of the vertex. Not its longitude, just how high up it is above the equator, off of these two pieces of information. Then once you have the latitude of your vertex, you can take the sine of the latitude of your vertex, divide the cosine of your course angle by the sine of the latitude of the vertex, and that will get you the sine of the DLO Vx. So using that starting angle and the latitude of your vertex, you'll be able to find how far away the vertex is from your starting point. And then let's say it comes out to be 50 degrees. You can then add 50 degrees to the longitude of the vertex, or subtract it if you're going east in the western hemisphere and west in the eastern hemisphere, etc. You apply your DLO V to get to where your vertex is, and then you have at that point the latitude and the longitude of the vertex. Now that you have the location of your vertex, you can actually build out your waypoint list. So obviously in the equation, you're plugging in the latitude of the vertex. That's obviously necessary to build out the list. And then here we have cosine of DLOVX. It's a ridiculous term there. Technically it's DLO little v little x, meaning the difference of longitude of the waypoint from the vertex. This is not something you need to calculate. This is something you choose personally. You get to decide exactly what this number is going to be. Because as I said before, you can find what the latitude of the waypoints are if you go 10 degrees away, and then if you go 20 degrees away, and then if you go 30 degrees away. You can then calculate the latitudes for each. So DLO Vx is that. It's 10 degrees, or it's 20 degrees, or it's 30 degrees. You will use this one equation multiple times and just change the DLO Vx to a new number to get further and further away from the waypoint. So you could build a location here, and here, and then here, and here, and then here, and here. And now that we're already so close to this one, we just build it out this way, here, and here, and here. So usually the most common practice is to use 10 degrees of longitude. Sometimes you can use 5, sometimes 20, but most of the time we just base it in units of 10. So if you were to do cosine of 10 times the tangent of LV, you would be moving 10 degrees on either side, and you would get the latitude of this point and this point. They have the same latitude. If you were to do cosine of 20, then you would get 20 degrees on either side, and you would get this point and this point. 30 on either side would get this point and this point. 40 on either side would get this point here, and then technically this point here, which is further away than your destination, so it doesn't matter and you can forget about it. And then 50 would get this point here. So you take this equation and you iterate on it, doing it multiple times to build out your list of waypoints, so that in the end you actually have a series of locations you can sail between to follow the Great Circle.